particle-wave duality leads to a phenomenon called the Heisenberg uncertainty principle, which is very commonly confused and often not very well explained. It's something that is actually really obvious if you think about the nature of waves and that waves can actually carry momentum. So let's take a look at it. Simply put, the Heisenberg uncertainty principle says that the uncertainty in a particle's position times the uncertainty in a particle's momentum is greater than or equal to a constant, in this case, Planck's constant divided by 4 pi. Planck's constant divided by 2 pi we call h bar because it comes up all the time and we got tired of writing it. But this is only weird if particles are behaving completely like particles. But if particles have a wave-like nature, it's very simple. Take this wave right here. Its momentum is proportional to its frequency, and because it's a nice, long, spread-out wave, it's very easy to determine this wave's frequency. But where is it? It's kind of everywhere, isn't it? Now look at this one. This one is not quite as everywhere, but its frequency would be harder to determine. It only exists for a shorter period of time, and it's a little more erratic, right? So the more we know about its position, the less we can know about its frequency. In the final extreme, check out this little blip. It's really easy to tell where it is, but what is the frequency of a single pulse? That's not a knowable number. It's almost a nonsense question. So we can know its position pretty much perfectly, but its momentum is a mystery. And so that's what that means. The uncertainty in position times the uncertainty in momentum is greater than or equal to a constant. It just has to do with the way waves wave. But there's something interesting, very interesting, about this equation too. The units of momentum times position are the same as the units of energy times time. So we can rewrite this equation as delta E times delta T is greater than equal to h bar over 2. And the consequences of this are very interesting. Okay, so the units are the same, but does that really mean anything? It turns out yes, it means something extremely important. The uncertainty in energy times the uncertainty in time is greater than or equal to Planck's constant divided by 2 tells us that conservation of energy on the smallest scale starts to get very fuzzy. It turns out that you can borrow energy from the universe as long as you pay it back fast. It's like the universe is an inattentive parent and you've decided to borrow money from, say, mom's purse. If you borrow a nickel, you can probably get away with that for a long time. She's not going to notice. If you borrow $1, you'd have to pay that back a little faster. If you borrow $20, you're going to have to pay that back pretty fast. If you take $1,000 out of mom's purse, if you don't pay that back really, really fast, you're going to be in trouble. The universe is a little bit like that. And as ridiculous as that sounds, it actually leads us to the nature of electric charge. It turns out that what electric charge is the ability to create photons that you don't have enough energy to create. You create photons, and those photons start to stream away from the charged particle, and then suddenly go, wait a minute, I don't have enough energy to exist, and poof, they're gone. These photons are called virtual photons because they don't have enough energy to exist on their own for very long. The more energy they have, the less time that they can exist, which means they have a limit as to how far away they can get at the speed of light. Super low energy photons can go really far, but very high energy photons can't go very far at all, which means that the stronger photons, the higher energy photons, are near the charged particle, and the weaker photons are much, much further away. Doesn't that mirror how the electric field works? The electric field is very strong close in, and then as you go outward, it weakens by 1 over r squared, right? And that's because the electric field is a cloud of virtual photons being created via the Heisenberg uncertainty principle, borrowing energy from the universe for a very short period of time, and then paying it back. That's what the electric field is, a cloud of virtual photons. So there you have it. The Heisenberg uncertainty principle seems so strange if you try and apply it to something like a tennis ball. What do you mean I can't know both where it is and where it's going and how fast at the same time? That's ridiculous, right? But if you apply it to waves, it's very simple. Where things get confusing is the particle-wave duality, where things like electrons, or even sometimes nuclei, can behave sometimes like a particle and sometimes like a wave. And so there's a lot of confusion and there's a lot of wishy-washy weirdness out there if you look up the Heisenberg uncertainty principle. But frankly, most of that comes from people not thinking about it in the right way. So I hope this helps break open the door to some of why quantum mechanics is weird, and to also take it and say, but yeah, it makes more sense than people like to say.